To build artificial intelligence today, computer scientists usually start from scratch, using artificial neural networks, a digital architecture loosely inspired by the biological brain. They create a system of connections that are initially random and unorganized. These artificial networks acquire their capabilities by consuming massive amounts of data from their environment. As they process this input, they detect patterns and organize their connections. The intelligence is entirely learned. A century ago, neurobiologists shared a similar outlook on the biological brain. They believed we were born as blank slates, with randomly wired networks that only gained meaningful structure through the experience of living. This model suggests that the specific biological details of how a brain builds itself are irrelevant to the final outcome, that the learning process alone is sufficient to create a functional system. Every autumn, millions of monarch butterflies spread across 3 million square miles of North America take flight. They travel up to 3,000 miles south, converging on a few specific overwintering sites in Mexico that cover less than a single square mile. When temperatures rise in the spring, they head back north, but they only make it a few hundred miles before they stop, mate, lay their eggs, and die. A new generation picks up the trail, continuing the journey for another few hundred miles. It usually takes 3 to 5 complete generations to finish the full round trip. This means the butterfly embarking on the 3,000-mile journey south in the fall is the great-great-grandchild of the one that last visited that precise tree. It is navigating toward a location it has never seen, using route knowledge it never learned. Sea turtles exhibit the same mystery, returning over thousands of miles to the exact beach where they were born, often many years later. If a biological network can execute complex logic without ever experiencing it, then our fundamental blueprint for building artificial intelligence is missing a critical piece. If the butterfly didn't learn the route, we might assume the map is hard-coded as a precise architectural blueprint within its DNA. This leads to the information problem. The genetic code contains remarkably little data compared to the staggering complexity of a fully wired brain. There is a severe mathematical mismatch between the starting instructions and the final product. There is no blueprint for brain connectivity in the genes. No hidden map and no biological GPS tells the neurons exactly where to go. Since the instructions aren't in the environment and aren't in the DNA, the necessary information must be generated during the physical process of growth itself. Before a brain can process data, it must physically assemble itself through a strict sequence of growth called self-assembly. We often imagine brain development like navigating the existing streets of a city, but that assumes the roads are already there. Biological self-assembly is more like navigating city streets while they are actively under construction. The map changes as the navigator moves through it, because the navigator's own movement is what causes the streets to be built. This growth is strictly sequential. Each new configuration of the brain serves as the mandatory physical foundation for the next step in the process. This transformation requires time and energy, resulting in a finished structure that contains vastly more information than the code that started its growth. In this model, biological intelligence emerges as the physical architecture itself, a structure forged step by step in space and time. Historically, AI research has tried to avoid these biological complexities altogether. The goal was to create an intelligent system without the messiness of physical growth. The underlying hope is that we can find a shortcut to intelligence by skipping the developmental phase and moving straight to learning. This shortcut relies on processing data through formal logic and blank slate networks, assuming we can replicate a mind through software alone. AI's progress has been defined by identifying which biological details can be safely classified as unnecessary to save on time and computing energy. Current AI models are incredibly successful, and they rely almost exclusively on this learning shortcut. But the monarch butterfly remains undeniable proof that some of nature's most complex behaviors do not come from learning. The inherited physical growth of a biological network provides a foundation for intelligence that data-driven learning may never be able to replicate. As we work towards artificial general intelligence, we have to ask what biological mechanisms we are wrongly discarding in our search for a shortcut. To build a system that truly rivals the biological brain, we may need to stop trying to program its connections and finally figure out how to let them grow.